this example will complete the shear center lectures. So far, we've looked at how to determine the shear distribution and shear center on elements that have vertical or horizontal orientation. In this example, you'll see how to tackle the same end goal for inclined segments as well. So for this cross-section shown, we'll assume that this is a cantilever beam with the applied load at the free end. And we'll also assume that our axes are the typical longitudinal X, vertical Y, so our cross-section axes would be the YZ. And we're also going to assume that the thickness is very thin, so the thickness is much smaller than the other dimensions. This means that for all practical purposes, we can ignore higher powers of t whenever they arise. We can take the center-to-center measurements as being the same as end-to-end measurements. So we know, first of all, because of symmetry, we only need to really consider one half of the section. So we'll consider the top half. And we know that because it is a free surface, the shear stress at A should be equal to 0. And based on the geometry given, with a 45-degree angle on member DE, the length of DE is A times the square root of 2. So the shear and moment diagrams for the loading and configuration given, we would have positive shear that is constant along the length of the beam, and our moment would be linear, starting with a negative value at the fixed end and 0 at the free end. So we'll start with the shear stress on segment AB. This is a vertically oriented element. We have vertical shear. In this case, B is equal to T. And our equation, shear stress is VQ over BIZ. So the area that we are going to use to calculate Q within this vertical segment, defined by the variable distance y from the neutral axis, is going to be the thickness times this distance here, which is 2a minus y, with the distance from the neutral axis to the top being 2a. So we can write this as v over I times t times 2a minus y times y1 bar as our Q, divided by t, and y1 bar, we'll define that. That's equal to y plus 2a minus y over 2, which is equal to 2a plus y over 2. So our shear stress is equal to V over 2IZ times 4a squared minus y squared. So we can calculate now the shear stress at A, verify that it's equal to 0. So at A, y is equal to 2a. Plugging that into our equation, we get shear stress at A is equal to 0. That checks out. At B, y is equal to A. Plugging that in, we get shear stress at B is equal to 3 over 2 V over IZ times A squared. And then the force in AB is found by taking the integral over the area of the shear stress. So since one dimension, t is constant, we can write that as the integral from a to 2a of vt over 2iz times 4a squared minus y squared dy. Evaluating this integral, we get 5 over 6 vt over iz a cubed. And the direction is in the same direction as shear, since we have positive shear along the entire length of the beam. We know that for the right face of a segment, which is what we're looking at, the shear stress direction would be downward for positive shear. So moving on to the next segment, horizontal element BD, we're going to have horizontal shear. Once again, our B is going to be taken as the thickness T. So here we're going to measure according to the coordinate z, the variable z, and you can take z as starting at either B or D, whatever is more convenient for the problem and your setup. In this example, I'm going to take z as being equal to 0 at D and increasing towards B. So shear stress is V over IZ times, we have our Q for the vertical segment, so AT times 3 over 2A plus A2 and Y2 bar. So the area A2 is now this segment here, which is the way we've defined Z, going to be A minus Z times T. And Y2 bar is just going to be A. That will be divided by the thickness T. So simplifying this a bit, the shear stress equation comes out to be V over IZ times 5 over 2 A squared minus AZ. Now, if you had taken Z to originate at B instead, you would end up with a different expression, but you should still get the exact same distribution. And as we confirmed last time, the shear stress varies linearly in the horizontal segment. So we can verify that that checks out. So we can calculate the stress at B. At B, Z is equal to A. So plugging that into our equation, we get shear stress at B is equal to 3 over 2 V over IZ times A squared. And this agrees with what we found earlier from the vertical segment evaluating the shear at B. So that checks out. At D, Z is equal to 0. So the shear stress at D is going to be 5 over 2 times V over IZ times A squared. And then the force in BD, we'll take the integral from 0 to A along the Z variable of VT over IZ times 5 over 2 A squared minus AZ dz. Evaluating the integral, we get 2VT over IZ times A cubed. And I've sketched the directions showing the direction of shear stress and force in BD here. This is just noting that because the beam is in negative bending, the top half of the cross section will be in tension. So that's the direction of the normal stresses. Now we'll tackle that diagonal element. So to find the shear stress in DE, first of all, we're going to use the same thickness for B in the equation. So this is going to be generally true regardless of the orientation. If you have a thin section and you're calculating shear stress, you use the thickness of the material. So we're going to assign a coordinate that is parallel with element DE. I'm going to call this coordinate S. And again, you can take the origin at either E or D. I'm going to take the origin at E. So Y3 bar, the distance from the vertical distance from the neutral axis to the centroid of the area, is equal to A times the square root of 2 plus S times 1/2 times 1 over the square root of 2, getting us to the vertical component of the length. So this is just the length along S, and then this gets us to the vertical component right here. Then the area A3 is A times the square root of 2 minus S times T. So plugging that into our shear stress equation, we get V over IZ times the area A1 and Y1, which is AT times 3 over 2 AT, plus Q2, which is AT times A, plus A3, which we just defined, A times the square root of 2 minus S times T, times Y3 bar, which is A times the square root of 2 plus S times 1/2 times 1 over the square root of 2. So again, that's Q1, that's Q2, and then we have A3 and Y3 bar. And then that's all divided by T. So, continuing with this, the shear stress then is V over IZ times 5 over 2a squared plus 2a squared minus s squared times 1 divided by 2 square root 2. And evaluating the shear stress at the corners at D, S is equal to A times the square root of 2. So plugging that in, shear stress at D is equal to 5 over 2 times V over IZ times A squared. And that checks out with what we got in our previous calculation. And then at E, S is equal to 0. So our shear stress at E is equal to 3.21 times V over IZ A squared. Then finding the force, FDE, we'll take the integral, and again we're working in that along the S coordinate line. So the integral from 0 to A times the square root of 2, the whole length from E to D, of VT over IZ times 5 over 2 A squared plus 2a squared minus s squared times 1 over 2 times the square root of 2 ds. Evaluating the integral, we get 4.2 times VTA cubed divided by IZ. And we can see here that from our shear stress equation, the shear stress varies quadratically along the diagonal member. So anytime it's not horizontal, basically, the shear stress will vary quadratically. So considering the directions of the forces on the entire cross-section. So considering the forces then on the entire cross-section, we have force in AB, force in BD, DE, and so on all the way through to the other end. And because of symmetry, we know that the values are going to be the same as their corresponding top half values. And to sketch the distributions, we'll just do the top half here. We know that at A, the shear stress at A is equal to 0 due to the free end, and it's going to vary quadratically in the vertical element to a value of tau B. And then the horizontal segment will start off at tau B and is going to increase linearly to tau D. And then inclined segment, we would have tau D increasing quadratically to tau E, at the neutral axis. So it doesn't really matter what side you sketch the distributions on. I just chose sides that made it very easy to clearly display what the magnitudes are, because that's all we're showing right now is the magnitude. The direction is noted by arrows, so you can include the direction like this. So just sketch the distributions so that they don't overlap, and if possible, and they're easy to tell what shape they are and label and everything like that. All right, so the next step then is to find the shear center. So we're going to assume a position for the shear center. So we'll assume the location is somewhere to the left of point E. Lowercase e is a distance from point E to the shear center, signifying eccentricity. So then we just sum moments about that point E. And going back to our diagram, again, remember that the distances are A, and A. And A. So some moments about E from those shear forces, since it's symmetric, we can just say negative FDE times E over the square root of 2 plus FBD times A minus FAB times 2A plus E. Multiply that by 2 and set it equal to 0. So multiplying it by 2 accounts for the bottom half. Because of the directions, the signs are consistent between the top half and the bottom half. So you just need to multiply by 2. So then we have 0 is equal to negative E times FDE over the square root of 2 plus FAB plus FBD times A minus 2FB FAB times A. So E is equal to FBD times A minus 2FAB times A divided by FDE over 2, over the square root of 2 plus FAB. And since we found values for FDE, AB, and BD, we can plug those in to get our answer in terms of the dimension A. So FDE is 4.2 times VTA cubed over IZ. FAB is equal to 5 over 6 times VTA cubed over IZ. And FBD is 2 VTA cubed over IZ. So, plugging those in, E is equal to 2 minus 2 times 5/6 divided by 4.2 over the square root of 2 plus 5/6 all times A, which calculates to be 0.08 0.76A. So now we've located that shear center as a pretty small fraction, about almost 9% of the dimension A off of that point E. And if you're wondering about this moment arm for FDE, we're just taking, just applying geometry there. So that's E divided by the square root of 2 to get, if you were to take the center line of DE, we're looking for that perpendicular distance, right, from that center line to the point E, or the shear center. So that's how that is determined. So you have E and then you just apply geometry to get E divided by the square root of 2 for that perpendicular distance. So this completes the lecture on shear center, and hopefully now you can apply this to homework problem 20.2.